My name is Jason Yim. I'm a third-year PhD student in EECS. My advisors are Regina Barzilai and Tommy Yakula. My research is focused on generative models for biology. In particular, I'm interested in protein design and using that in very impactful applications from medicine to climate change and enzyme discovery. So one of my recent projects was to apply generative AI to the generation of proteins. Recently, there has been a lot of new developments in generative AI. One such model is called diffusion models, where the idea is that you add noise to data and you train a neural network to extract the noise, to denoise it. We extended this to proteins using techniques that was in AlphaFold 2, where here we noise the proteins that AlphaFold 2 would see, and then we try to remove the noise there. And by doing this, we were able to generate new proteins that, one, were never seen before in nature, and two, were still very biologically plausible, as in they could become real proteins. So we developed this method, and we also took it to biological collaborators to make these artificial intelligence methods actually be useful in practice to biology and medicine. There we saw that we can generate new proteins using AI and also test them out in the lab that actually folded up into the structures that we wanted them to. And these can go on to be used in medicine to become vaccines or enzymes. So a protein has two sorts of angles that you look at it. One is that you can look at it as like a string, and along those strings are these like little beads. And these beads are called residues, and each residue is composed of some atoms. And so this bead, when a protein folds, is going to do like some sort of origami, and it's going to become a 3D shape, basically. And all of this is in 3D, it also has a 1D representation going throughout it. And so when we're injecting noise into this model, we're messing up the 3D coordinates of the protein, and we're asking the model to recover what those 3D coordinates are. The model knows that it has to be a string though, so we're trying to encode some sort of generalization that the noise has to respect this like a 1D structure of the protein. And so we do something called coarse graining to not have to model all of the atoms all at once, but kind of group some of the atoms together into the residues. And so we use something called a frame, where there's a translation and a rotation component to each residue. And along this 1D chain, the frames have to be aligned in a way. So this simplifies the machine learning problem, and we developed a way to inject noise properly into this 1D and 3D representation of the protein to train a neural network to generate the protein. It can take billions of dollars and lots of years to generate a new drug. And a lot of this has to come down to first coming up with a possible protein or a possible drug that can hit a disease, and also optimizing that drug protein. And a lot of this in the past there has been very slow to do, but with AI we can potentially accelerate that path of how pharma and a lot of companies make drugs. At the same time, there are a lot of diseases that are undruggable, as in small molecules cannot be used to hit the targets, but proteins kind of enables a new way to come up with brand new therapeutics that aren't currently available or currently even possible. And for the ones that we already have, the cost of creating those proteins can be very high, so this sort of technology can drastically bring down the price and come up with maybe simpler proteins that can be manufactured a lot easier. So for the rest of my PhD, there are still some technical questions that are unanswered, and I would like to solve those. After PhD, I'm hoping to either go to academia or industry to possibly do a startup. If I had an ideal world, I would experience both.